What if I told you that the next great leap in computing power, the one that will fuel a new generation of artificial intelligence, create virtual worlds indistinguishable from our own, and solve problems we once thought unsolvable, isn't just about making things smaller? What if it's about fundamentally changing the shape of how we build them? For decades, the path forward was simple: shrink, shrink, shrink. But we've hit a wall built by the laws of physics itself. And to get past it, the brightest minds in the world had to learn how to bend reality. Today, we're diving deep into the heart of the semiconductor industry, into the pristine, near-magical clean rooms of TSMC to uncover the story behind their revolutionary into-process node. This isn't just an incremental update. This is a paradigm shift built onto monumental innovations. One you might have heard of, the other has been a secret revolution hiding in plain sight. Welcome to the story of how we traded straight lines for impossible curves, and in doing so, unlocked the future. When you hear about a new chip from Apple or Nvidia, the conversation usually revolves around the process node 7 nanometers, 5 nanometers, and now, the frontier of 2 nanometers, or N2. For most of us, these are just numbers that get smaller, meaning our devices get faster and more efficient. But within N2, TSMC has done something far more profound than just shrinking the map. They've redrawn it completely. This leap forward is powered by two pillars of innovation. The first is a radical redesign of the transistor itself, the fundamental building block of all modern electronics. For over a decade, we've used a design called FinFET. Think of it like a light switch where the gate, the part that turns the current on and off, sits over the channel like a saddle on a horse, touching it on 3 sides. It's been a workhorse, but at these new, impossibly small scales, it's getting leaky. Current is starting to seep through even when the switch is off. TSMC's N2 introduces the solution, the gate-all-around GAA transistor. Instead of a fin, the channel is now a series of incredibly thin nanosheets, stacked like microscopic sheets of paper. The gate material then wraps completely around these sheets. Imagine going from gripping a rope with 3 fingers to wrapping your entire hand around it. The control is absolute. This is the first fundamental change to transistor architecture in over 15 years, a true hardware revolution that promises to slash power leakage and boost performance. But if GAA is the powerful new engine, the second innovation is the revolutionary navigation system guiding it. It's a change so subtle yet so powerful, it is happening in the one place you'd never think to look, the stencils used to print the chips. For the first time at this scale, TSMC is embracing curvilinear masks, photomasks that use smooth, flowing, organic curves instead of the rigid, blocky, straight lines we've used for half a century. This might sound like a simple aesthetic choice, but it's not. It represents a silent but seismic shift in manufacturing philosophy. This is the gateway that finally allows the immense parallel processing power of GPUs, the very chips these masks help create, to become a core part of the manufacturing process itself. It is a self-fulfilling prophecy where AI chips are now helping to design and build the next generation of AI chips. What was once a fascinating theory in academic papers is now the bedrock of TSMC's into production. And the story of how we got here is a saga of fighting physics, breaking old rules, and inventing machines that were once thought impossible. To understand why curve masks are such a big deal, you first have to understand the sacred, almost mystical process of how chips are made, photolithography. At its core, the concept is surprisingly similar to old-school film photography. You start with a pristine, perfectly circular silicon wafer, which is like your photographic paper. You coat it with a light-sensitive chemical called photoresist. Then, you place a photomask between the wafer and a powerful light source. This photomask is your negative. It's a quartz plate, perfectly flat and impossibly clean, with an opaque pattern of chrome on it that represents one layer of the chip's intricate circuitry. When you flash the light, it passes through the clear parts of the mask and exposes the photoresist on the wafer below. The exposed or unexposed, depending on the process resist, is then washed away, leaving a pattern. This pattern is then etched permanently into the silicon layer. You repeat this process layer by layer, sometimes over 100 times, with a different mask for each layer to build up the complex three-dimensional city of transistors and wires that make up a modern microprocessor. Now, here's where it gets crazy. That photomask isn't just a stencil. It is one of the most valuable and technologically advanced artifacts on the planet. A single mask can take days to create and cost hundreds of thousands of dollars. A full mask set for a high-end chip containing all the different layer patterns can run into the tens of millions of dollars. These aren't just expensive, they are impossibly fragile and sensitive. The mask shops, as they are called, are some of the most controlled environments on Earth. They are shielded from seismic activity, electromagnetic interference. Even subtle variations in the Earth's magnetic field can throw off the electron beams that write the patterns. The air is filtered to a degree that makes an operating room look dirty. A single stray dust particle, 1,000 times smaller than a human hair, landing on the mask during its creation could be a fatal defect. That defect would then be printed onto every single chip on the wafer, and every wafer after that, potentially ruining millions of dollars worth of product. And these masks hold the crown jewels of the tech world, the intellectual property, the secret sauce of companies like Apple, Nvidia, and AMD. The design for the next iPhone processor or the next world-changing AI accelerator is physically encoded on these plates of quartz. The pressure on the mask shop is therefore absolute. They are tasked with achieving a level of precision that borders on the divine, because the world's technological progress depends on it. For decades, Moore's law chugged along, driven by a simple principle: to make the features on a chip smaller, you just needed to use a light with a shorter wavelength. It's like trying to draw a fine line. You can't do it with a thick magic marker. You need a pen with a very fine tip. In lithography, the wavelength of light is your pen tip. We went from visible light to ultraviolet UV, then to deep ultraviolet DUV. But as we tried to print features measured in the dozens of nanometers, a fundamental problem of physics reared its head: diffraction. Light doesn't always travel in perfectly straight lines. When it passes through a very small opening like the patterns on a photomask, it behaves like a wave and tends to spread out, blurring the edges. Imagine trying to create a sharp shadow of your hand using a fuzzy, out-of-focus light source. The edges of the shadow will be soft and indistinct. In chipmaking, this is catastrophic. A line that was supposed to be a sharp 20 nanometer wide wire might print as a fuzzy 25 nanometer wide smear. Two lines that were supposed to be separate might blur together. The obvious solution was to once again jump to a much shorter wavelength. And we did, with extreme ultraviolet or EUV light. But developing EUV was one of the most complex and expensive engineering challenges in human history. It took over 2 decades and billions of dollars. So, in the meantime, the industry had to get clever. They developed a bag of tricks called resolution enhancement techniques (RET). The most important of these is optical proximity correction, or OPC. The idea is brilliant in its simplicity. If you know the light is going to blur the corners of a square, why not pre-distort the square on the mask to compensate? The mask pattern might end up having little serifs or hammerheads on the corners. When the blurry light passes through this weird, pre-distorted shape, the resulting image on the wafer blurs back into the perfect square you wanted all along. Engineers also started adding sub-resolution assist features, tiny shapes on the mask that are too small to ever print themselves, but their presence next to a main feature helps to bend the light in just the right way to make the main feature print more clearly. It's like using unseen guide wires to make sure a kite flies straight. These techniques were ingenious, but they were fundamentally corrective. They were a patch on a system that was being pushed far beyond its natural limits. A more radical solution was needed.
What if instead of starting with the design you want and then applying corrections to the mask, you did the entire process in reverse? This is the mind-bending idea behind Inverse Lithography Technology (ILT). With ILT, you start with the perfect, ideal pattern you want to see on the silicon wafer. Then, you use incredibly complex physics simulation software to calculate backwards. You ask the computer, Given the physics of my light source and lenses, what would the photomask have to look like to produce this perfect result on the wafer after all the inevitable blurring and diffraction? The answer the computer comes up with is bizarre. It's not a slightly corrected version of the original design. It's often a completely alien, free-flowing, organic-looking pattern. It's full of curves, disconnected shapes, and squiggles that bear no resemblance to the final circuit. These ill-generated masks are often described as looking psychedelic. They are the ghostly, mathematically perfect inverse of the final product. And they work astonishingly well. By designing the mask this way, you dramatically expand what's known as the process window. Think of the process window as the set of conditions, focus, exposure, energy, etc., within which you can successfully manufacture a chip. A small process window means that the slightest vibration or temperature fluctuation can ruin your yield. ILT creates masks that are inherently more robust. The resulting patterns on the wafer are less sensitive to these small manufacturing variations, leading to higher yields, more reliable chips, and ultimately, lower costs. ILT was hailed as a theoretical masterpiece. It was the ultimate expression of computational lithography. But for years, it remained just that, a beautiful theory. Because there was one massive, insurmountable problem. We had no way to actually build these beautiful, curvy masks. The machines that write photomasks are marvels of engineering. For decades, the industry standard has been the variable-shaped beam VSB mask writer. It works by firing a beam of electrons at the mask blank, which is coated in an electron-sensitive resist. The beam itself is shaped by passing it through to square apertures. By offsetting these apertures, the machine can create a square or rectangular shot of electrons of varying sizes. It can also create 45-degree triangles by using triangular apertures. And that's it, squares, rectangles, and 45-degree triangles. This limitation forced every single chip design in the world to be drawn using only horizontal, vertical, and 45-degree lines. This became known as Manhattan geometry because the resulting layout looked like the grid-like street map of Manhattan. Now, you see the problem. ILT wants to create beautiful, flowing, psychedelic curves. But the VSB writer, the workhorse of the entire industry, can only draw blocks. The only way to create a curve was to approximate it, a process called Manhattanization. You would break the curve down into thousands, or even millions, of tiny little rectangles, like trying to build a circle in Minecraft. This was a terrible compromise. First, you lose all the fine detail and smoothness of the true ILT solution. The approximation is never as good as the real thing. Second, the data file for the mask becomes astronomically large. Instead of describing one elegant curve, you have to describe a million tiny boxes. This requires massive amounts of processing time. And third, and most critically, it slows the mask writing process to a crawl. The VSB writer has to physically draw every single one of those millions of little rectangles, one shot at a time. A mask that might have taken 10 hours to write could now take 100 hours or more. In the high-volume, fast-paced world of semiconductor manufacturing, this was a non-starter. ILT was a genius solution trapped in a world that could only think in straight lines. The dream of curvilinear masks was dead on arrival until a new kind of machine emerged. The bottleneck wasn't the idea, it was the tool. The single electron beam of the VSB writer was like trying to paint a mural with a single, tiny paintbrush. What if, instead, you could use a tool that worked like a high-definition digital display, where you could control millions of pixels all at once? This is the revolutionary concept behind the multi-beam mask writer MBMW. Instead of a single, shaped beam, a multi-beam writer starts with a broad, powerful electron beam and passes it through a special plate that splits it into a grid of hundreds of thousands of tiny, individual beamlets. Think of a 512 by 512 grid that's over 262,000 tiny beams, all acting in parallel. Each of these beamlets can be independently turned on or off, or even modulated in intensity by a complex electrostatic deflection system. The machine then scans this massive pixel grid across the surface of the photomask. It's no longer drawing shapes. It's printing the masked pattern pixel by pixel, much like an inkjet printer, but with electrons and at an atomic scale. The impact of this was earth-shattering. Suddenly, the complexity of the shape no longer mattered. A smooth, complex curve was just as easy to print as a simple straight line because you were just turning the right pixels on. The right time was no longer dependent on the number of geometric shapes, but simply on the area of the mask. This completely severed the Gordian knot that had tied ILT to Manhattanization. With multi-beam mask writers, the impossible-to-manufacture psychedelic designs from ILT software were suddenly, miraculously, possible. The theoretical dream could finally become a physical reality. This breakthrough wasn't the work of one company, but the result of a fierce competition between two rivals on opposite sides of the globe. The undisputed leader in the multi-beam space is an Austrian company called IMS Nanofabrication. Their story is a masterclass in strategic pivots and long-term vision. IMS didn't originally set out to build mask writers. They were pioneers in a different technology called ion projection lithography. But as the industry's needs shifted, they saw the writing on the wall and pivoted their immense expertise in charged particle optics towards developing a multi-beam electron system. They began their research early, giving them a crucial head start. They formed a strategic partnership with JEOL, a Japanese giant in electron microscopy, to build the physical machines. But the final piece of the puzzle came from an unlikely source. Intel. In 2009, Intel's venture capital arm invested heavily in IMS, and later, in 2012, Intel acquired a larger stake. This infusion of cash and, more importantly, industrial validation supercharged their development. The timing was perfect. Just as the industry was beginning its painful, expensive transition to EUV lithography, it became clear that the new EUV masks would require far more complex patterns like ILT to work correctly. The need for a better mask writer went from a nice-to-have to an absolute, existential necessity. IMS was ready. They rolled out the first commercial multi-beam systems, and they quickly became the gold standard, the enabling technology that the entire leading-edge ecosystem, including TSMC and Samsung, would come to depend on. But IMS wasn't alone. In Japan, another company was watching closely. Nuflor Technology, a spin-off from the venerable Toshiba machine, had a long and storied legacy in building conventional VSB mask writers. They were the incumbent, the established power. Seeing the threat and opportunity of multi-beam, they launched their own crash development program. In a stunning display of engineering prowess, Nuflor managed to develop and demonstrate their own multi-beam system just 1 month after IMS showcased theirs. The race was on. This rivalry between the Austrian pioneer and the Japanese giant was incredibly healthy for the industry. It pushed both companies to innovate faster, improve their machines' throughput and resolution, and ultimately brought the cost and accessibility of the technology to a point where widespread adoption became feasible. This fierce competition is a key reason why the technology matured so quickly, arriving just in time for the inter-revolution. So the puzzle was almost complete. We had the brilliant software theory ILT and the revolutionary hardware to write it MBMW. But there was one final, gargantuan hurdle: the sheer computational horsepower required to run the ILT simulations. Calculating the perfect, psychedelic masked pattern for an entire chip is one of an MBMW. The physics simulations are so complex that a single mask set for a modern chip could require millions of hours of CPU computing time. A single high-end server farm would need to run for weeks, or even a month, just to generate one design. This was a paralyzing bottleneck. You can't run a multi-billion-dollar fabrication plant if you have to wait a month for your R&D team to design the next mask. This is where the story comes full circle. The solution to this computational crisis came from the very industry these masks were being designed for: high-performance computing, specifically the GPUs, like the ones made by Nvidia, are designed for massively parallel workloads. Instead of having a few very powerful CPU cores, they have thousands of smaller, simpler cores that can all work on a piece of a problem simultaneously. This architecture is perfect for things like graphics rendering, scientific simulation, and, as it turns out, the physics calculations of inverse lithography. Companies like D2S, a pioneer in the space, started building software to offload these calculations to GPUs. But the true game changer was Nvidia's own entry into the field with its QLitho software library. Nvidia, being the master of its own hardware, built a computational platform that could take the lithography simulation process and accelerate it by an incredible margin. The results are staggering. A workload that took 2 weeks to run on a fleet of 40,000 CPU cores could now be completed in just 8 hours using 500 Nvidia H100 GPU systems. The bottleneck was not just eased, it was obliterated. This was the final enabling piece. With the computational power of GPUs unleashed by software like QLitho, TSMC could finally deploy full-chip, curvilinear ILT masks at the scale and speed required for high-volume manufacturing on its node. The symphony was complete. GAA provided the new instrument, ILT wrote the complex music, MBMW was the orchestra that could play it, and GPUs were the conductor, making it all happen at tempo. And so we arrive at TSM Season 2. It is the culmination of this incredible journey, a convergence of breakthroughs in physics, engineering, and computer science. It marks the true beginning of the era of curvilinear manufacturing. It's no coincidence that this technology is coming of age now. The driving force is the insatiable demand for AI chips. These processors are so complex, and the profit margins on them are so high, that companies like Nvidia are willing to justify the enormous expense and R&D effort required to pioneer these cutting-edge techniques. The gains in performance and power efficiency are worth the cost. But what starts with high-end AI chips will eventually trickle down. The innovations and cost reductions from this new era of manufacturing will find their way into the processors in our smartphones, our cars, and our laptops, improving the entire semiconductor value chain. And the most exciting part, we are just scratching the surface. Even on N2, the full potential of ILT and curvilinear design is not yet being exploited. There are still compromises and approximations being made. As the software gets smarter, the multi-beam writers get faster, and the GPUs get more powerful, we will be able to create even more optimal, more psychedelic masks, unlocking further gains in performance and efficiency that we can't even imagine today. The story of the curved mask is more than just a tale of technology. It's a profound lesson in problem solving. It teaches us that when you hit a fundamental wall, the solution often isn't to push harder, but to step back and change the very shape of your thinking. It shows us that progress is rarely a single breakthrough, but a convergence of innovations across hardware, software, and process, all coming together at the right moment. When our tools could only draw straight lines, we were limited to a world of grids. But by inventing tools that could draw with the freedom of nature, we unlocked a new dimension of possibility. This journey reminds us that the greatest barriers are often the assumptions we hold about our own limitations. The engineers who were told you can't build curvy masks didn't listen, they built a new machine. The designers told you can't compute that fast didn't listen. They found a new way to compute. That is the spirit of innovation that powers our world. So the next time you use a device powered by a cutting-edge chip, remember the invisible revolution that made it possible. Remember the psychedelic patterns, the million tiny beams of electrons, and the symphony of computation that bent the laws of physics to its will. What other impossible problems in our world, whether in medicine, energy, or exploration, do you think are just waiting for a similar convergence of breakthroughs? Where is the next Manhattan geometry in our thinking that needs to be shattered? I'd love to hear your thoughts in the comments below. Thank you for joining me on this journey into the heart of the chip. I wish you all the best of health, and I hope you'll continue to stay curious. If you enjoyed this deep dive, please consider liking this video and subscribing to the channel for more stories from the frontiers of science and technology. We'll see you next time.